Okay, so suppose we have this sequence of so we have sequence of complex valued function in some domain A, so it was C. Okay, so clearly for each z belongs to A, fn z is basically this is a sequence of complex numbers. Okay, so we define the pointwise convergence. Okay, so let fn be a sequence of complex valued functions. So fn said to be pointwise convergent. If for every z belongs to A, fn z is basically is convergent sequence of complex numbers. So this is the way we define the pointwise convergent. Okay. So okay, so whatever the limit is, now define a function. Define a function f such that A to C by so f of z is basically limit n tends to infinity fn z. Okay, because this is a sequence of complex numbers, so this will convergent because f is pointwise convergent. So we define this function. So we say that basically say that fn converges to f pointwise. Okay. Okay, fine. So these are the basic things. One can go through any book. Now let us talk about uniform convergence. Okay. So let again fn such that A to C be a sequence of functions. Okay. So we say fn converges to f uniformly on A if for every epsilon positive there exists a natural number n naught such that for every z belongs to A, mod of fn z minus f of z is less than epsilon for every n greater than or equals to n. Okay, so this is the definition of uniform convergence, and observe that here this n naught only depends upon epsilon. So I will write as note. Okay, so here n naught only depends upon epsilon, not on point set. Or we can also also. Okay, so now we have this theorem. So let fn says that a to c be a sequence of continuous function, okay, continuous function for each n, okay, and fn converges to f uniformly on a, okay. So the theorem is then f is continuous, okay. F is continuous. Moreover, integral over gamma fz dz is basically limit n tends to infinity integral over gamma fnz dz. Okay, so this is the theorem. Okay, so I want to inform that today's extra session, and I'm discussing about space of analytic functions. Okay, so I have to start with pointwise convergence and uniform convergence. So we'll slowly go. So we're slowly going to see about space of analytic functions. Okay, this is there for every rectifiable, or you can say piecewise smooth curve gamma. Okay, so, for the proof, okay, so proof of this part. So just to show that f is continuous once your function fn is converges uniformly on a. So this is, I mean, this is standard fact. One can find in any book on this topic. So we will try to prove this one. Okay. Okay. So let gamma be any piecewise smooth curve. Piecewise smooth curve. Okay. So I will choose epsilon as 1 plus length of this gamma. Okay, let us take this epsilon in this form. Okay, so since fn converges uniformly, okay, so okay, so since fn converges uniformly, so for this epsilon there exists some capital N, okay, such that just wait a minute, such that for every z we have fn z minus f of z is less than epsilon upon 1 plus length of gamma for every n greater than equals to n. Okay, this is we have. Okay, now we have to prove this thing. Okay, so consider this thing. So you take inte integral over gamma fn z minus integral over gamma fz dz. Okay, so this also can be written as integral over gamma fn z minus f of z dz. Okay, now so this is now so integral over gamma fn z minus f of z dz. Now this is less than equals to integral over gamma modulus of fnz minus f of z into mod dz. Okay, now use this inequality. Let us say this inequality as star. Using star, we have, so, integral over gamma fnz minus f of z dz is less than equals to, so this will be epsilon upon 1 plus length of gamma integral mod dz. Okay, so so this will be epsilon upon 1 plus length of gamma into length of gamma, which will be less than epsilon. Okay, so, and this is for uh, okay, so for n greater than equals to n, consider the following. Okay, so for n greater than equals to n, what we get, integral over gamma fnz minus f of z dz is less than epsilon. Now what does it mean? So as n tends to infinity, this thing will tends to 0. Okay, so we get, so we basically prove that limit n tends to infinity integral over gamma fnz is basically integral over gamma f of z. So I hope it is clear. Is it fine? Okay, so I assume that is okay. Okay, now we will see about uniform Cauchy sequence. Okay, so let fn says that a to c be a sequence of functions. So the sequence fn is called uniform Cauchy sequence if for every epsilon greater than 0 there exists n which depends only upon epsilon, such that for every z belongs to a, we have fnz minus fnz is less than epsilon for all m comma n greater than equals to n. Okay, okay, so note here that, okay, no, so we'll prove the following theorem. I mean, we'll see the following theorem, which gives if and only if criteria of uniform convergence. Okay, so which is known as Cauchy criteria of uniform convergence. So Cauchy for uniform convergence. Okay, so let fn converge. Okay, sorry. Fn says that a to c be sequence of functions. Okay, so then fn converges to some f uniformly uniformly on A. So if and only if, basically Fn is a uniform Cauchy sequence. Fn is a uniform Cauchy sequence. Okay, so this is the criteria. Okay, and this is again a standard fact. Okay, so we'll move towards the next thing, which is quite important in the case of space of analytic functions, which is known as the normal convergence. Okay. Okay, so let omega be, let us say, a domain, or you can also take open set domain in C. Okay, so there is a notion of this and Fn says that omega to C be sequence of functions. Okay, so there is a notion of convergence of the sequence Fn, okay, which lies between pointwise convergence and uniform convergence and uniform convergence. Okay, so definition is like this. So Fn converges normally in omega. So I should write like, so Fn converges to F normally in omega if Fn converges to F uniformly on every compact subsets of omega. Okay, so this is a definition. I mean, for example, if you see, uh, let us say, for example, if you see Fn from unit disk to C, Fn defined by z to the power n. So Fn is pointwise convergent, but not uniformly convergent on D. This you can see. I mean, in the case, in the real case, you can see that Fn x to the power n. If you take x belongs to the 0, 1, so Fn is not uniformly convergent on 0, 1. Okay, but on every compact subset of 0, 1, Fn is uniformly convergent. So similarly for this one also, Fn is uniformly convergent on every compact subset of D. Okay. Okay, so okay, so these kind of results holds for this one also. I mean, this kind of results holds for normal convergence also. Okay, so I will just write it down, a proposition or lemma, you can say. Let us write it down. So Fn such that omega to c, Fn converges to f normally normally in omega if and only if so Fn converges to f uniformly on each closed disk. So you don't need to take arbitrary compact set. Means you don't need to check on every on arbitrary compact set. You can just take the closed disk. Each closed disk contained in contained in omega. So this thus reduces the uh, this compactness. I mean, you don't need to check on every compact set. You just check on closed disks. Okay. Okay. So the following theorem again true, like we have in the case of uniform convergence. So suppose suppose Fn such that omega to c be sequence of continuous functions and Fn converges to f normally in omega, then f is continuous on omega. Further, integral over gamma fz dz is basically limit n tends to infinity fz dz. Okay, for every rectifiable curve gamma in omega. Okay. Okay. Now we will talk about first space of continuous functions. So now we are going to talk about space of continuous functions. Okay, so let omega subset of C be a domain. Okay, so like if you want to consider consider the collection of all functions, complex valued functions, which are continuous on omega. Okay, now we want to define a metric on this set so that we can say that this is a space, I mean a vectoric space. Okay, now in the if you see in the real case, if you have like if you take the collection of functions from close interval a comma b to r, collection of all continuous functions, this thing, then then you know how to define the metric on this one. You just take the supremum. Okay, distance between 2 points is as f minus g, and supremum you take, okay, z over ab. But here the problem is this is a domain. Okay, so you cannot just take the supremum. Supremum may not exist. Okay, so for that we need a different notion. Okay, so what you are going to do is consider the set c omega as f such that omega to c such that f is continuous. Okay, so this is your set. We want to define a metric on this. We want to define a metric on c omega. Just to recall, okay, if you're if you consider c a comma b, okay, so it is f such that a comma b to r such that f is continuous. So So we define a metric on basically d of f comma g as supremum of f minus g of x. Okay, this we define. Then in this case, this is a standard fact. This is basically a metric space, and in a sequence fn, in this one converges to f in this metric space. Okay, so d conversion. Okay, so fn converges to f with respect to metric d if and only if, this we know, if and only if fn converges to f uniformly. Okay, so what we want to do, we will define a metric on c omega, and we will see which type of convergence it will give. We have seen pointwise, uniform and normal convergence. So we will see which kind of convergence we will get. Okay, so here's a proposition how to define a metric that will help us. So proposition, it is, let, so if omega is, so this is, so this proposition from this proposition for any open set is open in C, then there is a sequence Kn of compact subsets of omega such that basically omega is complex subset. Omega is basically can be written as n equals to 1 to infinity this Kn. Okay, moreover the set Kn can be chosen to satisfy the following conditions. Following conditions. So A is Kn subset of interior of Kn plus 1. B is K subset of omega, and K is compact. So you take any compact subset of omega, then K is subset of Kn for some n. Okay, so we can choose this sequence Kn. Okay, so so its proof one can go through conway conway book. Conway book. Okay, okay, so for example, if we see the case of omega is, let us say, d. Okay, so how do we choose Kn? So let us say z belongs to d such that a mod of z minus z is less than, we can say z is less than equals to 1 minus 1 by n. Okay, or you can also say, so 2n. So this is for n greater than equals to 1. So we can say that union of Kn n equals to 1 to infinity. So at n equals to 1, it is 1 by 2, and again as n equals to, so this is, wait a minute, just wait a minute. So at n equals to 1, so k1 is your basically mod z is less than equals to 1 by 2. Okay, k2 is basically your So let us say so this is mod z is less than equals to 3 by 4. Okay, so this will cover the unit disk. Okay, also do we have this thing? So kn is a subset of interior of kn plus 1. So kn is subset of interior of kn plus 1. Okay, so if you see k1, so k1 is your so k1 is obviously a subset of interior of kn k2. Interior of k2 is nothing but mod z is less than 3 by 4. Okay, this is true. And if you take any compact set k, that will be in some kn. Also any compact set k subset of omega, k is basically subset of kn for some n. Okay, so this is true. Okay, so this is fine. Using this one, we will define a metric on this one. So how do we define? So we'll first define a sequence of uh, this metric. So so define rho n of f comma g as supremum of modulus of fz minus gz. Okay, where z belongs to kn. So this we define. Okay, now define define a metric on omega. Sorry, this is c omega by so rho of f comma g is basically summation n equals to 1 to infinity 1 upon 2 rho n of f comma g upon 1 plus rho n of f comma g. One can see that this will always, oh sorry, this will always converge. Okay, so now this has some properties you can check. All these are given in Kanban book. So C omega with this one is basically is a metric space. Furthermore, you can see that C omega this is a complete metric space. Complete metric space. Just wait a minute. Okay. Now one more thing is that third thing. This also one can see the proof. So Fn converges to in this metric rho metric to a function f if and only if Fn converges to f normally in omega. So this is the criteria of convergence. So this is how a convergent sequence looks like in this metric space. So we say that a sequence is convergent in this metric space if that is converges normally. If that converges normally. Okay. So this is done. Let us talk something more. Okay, just wait. So now we have a. So now we can talk about. Now we can say that this is space of continuous function because now we have a metric space structure on this one on this set. Okay. So okay. Next definition we will see. f, which is a subset of c omega, is normal in omega if each sequence, let's say fn, in f has a subsequence which converges which converges which convergence. I mean, I can just say that each sequence fn in f has a subsequence which is convergent. What does it mean? It means that it converges normally, which converges normally to uh, limit function, let us say, whatever it is, limit function f in omega. Okay, that is uh, that is there exists a subsequence f and k, okay, such that f and k converges to some limit function f uniformly uniformly on every compact subset of. So this is known as a space of a set is said to be normal. Okay, so a set is said to be normal if each sequence in f has a subsequence which is convergent in this metric row, that is, which is converges normally. Okay, which means which converges uniformly on every compact subset of omega. Okay, one thing to note down is that, see, this definition is basically looks like the sequentially compactness. Okay, but there's a difference when we say f is a normal and f is sequentially compact. So in the case of sequentially compactness, that limit function also belong to that set. In this case, this may not be the case. So that is the difference between normal family and sequentially compact family. So, so the limit function of subsequence is not required to be in the set. Okay, okay, so okay, now let us talk about eq continuity. Okay, so a set f subset of c omega is equicontinuous at a point z naught belongs to omega if for every epsilon greater than 0 there exists a delta positive such that for z minus z naught is less than epsilon, we have for every f belongs to this one, modulus of fz minus f of z naught is less than epsilon. So we say that uh, a subset f or a family f is equicontinuous at a point z naught if we have this thing. Okay, so observe that here this delta depends only upon this epsilon. Okay, it doesn't depend upon this family, this function in this family. Okay, so this same delta will hold for all f. So we say equicontinuity at a point. Also, we say this as a pointwise equicontinuous. Okay. No. So pointwise equicontinuous we say on omega if it is equicontinuous at every point of the omega. Okay. So let us see the next thing. Definition. So when f is equicontinuous equicontinuous at every point every point of omega, we say f is equicontinuous in omega. Okay, fine. So now we have this thing. Let me just say here. Yeah. Okay. Okay. So this is a pointwise equicontinuity. Now we'll talk about something uniform equicontinuity. So this is related to uh, okay. So just wait a minute. Okay. So we say f is uniform equicontinuous over a set. Wait. Yeah. So we say over subset. Let us say e of omega if for every epsilon greater than 0 there exists delta greater than 0 such that for all z comma z dash in E with mod of z minus z dash is delta, we have for every f belongs to f mod of fz minus fz dash is less than epsilon. Okay, so this is definition of uniform equicontinuous. Okay, we will see a criteria when pointwise convergence, pointwise uniform convergence implies equicontinuous. Okay, so this is kind of, you can see the proposition. Okay, so suppose f subset of c omega is equicontinuous continuous at each point of omega, that is f is pointwise equicontinuous continuous. Then basically f is uniform equicontinuous over each compact subset of omega. So this is quite useful result. Okay. Now the next two theorem which are going to talk about. So this basically says that if you have a pointwise, uh, if you have a family which is pointwise equicontinuous on omega, then basically it is uniformly equicontinuous over each compact subset of omega. Okay, this is quite easy to prove. One can prove. Okay, Okay, so now we will see. Okay, so now we will see when we have this. Now we see a relation. How equicontinuity is related to uniform conversion, and when uniform convergence implies equicontinuous family. Okay. Okay, so we'll talk about this theorem. Okay, so suppose f is a family of continuous functions on omega is equicontinuous. So I meant to say pointwise equicontinuous. Pointwise equicontinuous on omega. Let Fn be a sequence in F, and suppose Fn converges to F pointwise in omega, then Fn converges to F normally in omega. So once you have a equicontinuous family, it implies that it implies once you have equicontinuous family, pointwise convergence implies the normal convergence. I mean uniform convergence on every compact sets. Okay. So this is one thing important to know. Other is the converse of this one. Okay. So this is the one thing which is important. So once you have a equicontinuous family, pointwise convergence implies the normal convergence. Okay. Other theorem is, which is again important. So again let F be family in C omega, and suppose Fn converges. Okay, so Fn converges to F uniformly on omega, then this Fn is basically uniformly equicontinuous over each compact subset of omega. Okay, so now we are moving towards the Argyll-Asoli theorem. So this, okay, but before this one, I would like to define some terminology which will be used to state this theorem. So one such thing is pointwise bounded, which is so a set, so a family F subset of C omega is pointwise bounded in omega if for each if for each fixed z in omega, the set S F set such that F belongs to this family is a bounded set of complex numbers. Okay, quite clear. This definition is quite clear. Okay, so this is pointwise bounded. Next thing is uniformly bounded. So f, again, all those things, omega is uniformly bounded in omega if there exists m positive such that mod of fz is less than equals to m for every z belongs to omega and for every f belongs to, okay, next term is locally bounded. So a family f in C omega is locally bounded in omega if for each point z belongs to omega there exists m and r positive such that for every f belongs to this omega mod of fz is less than equals to m for mod z minus, okay, so for every z naught is less than r. Okay. So it means that f is said to be locally bounded. It means that a family f, I mean, so a family f is said to be locally bounded in omega if at every point of omega, I mean around, so at every point there is a neighborhood, okay. It means that around every point of z naught belongs to omega, f is uniformly bounded, okay. So f is locally uniformly bounded. So this is the ball, I mean, so now one can, so this lemma is, okay, so this lemma is that a set omega is locally bounded if and only if for each compact set k subset of omega there exists a constant m which only depends upon this compact set k such that mod of fz is less than equals to m for every z belongs to omega, oh sorry, so for every z belongs to k and for every f belongs to f, okay, that is this family f is uniformly bounded on k. So I said f is locally bounded if and only if the family f is uniformly bounded on every compact set k. Now we will state the generalization theorem. Okay. So this gives a equivalent criteria for being a normal family. Normal family I've already defined. Okay, so wait a minute. Yeah, this is the normal family I've already defined. So Ajala-Asori theorem says that a family f omega is normal in omega if and only if and only if f is equicontinuous and pointwise bounded the main theorem. Okay, also theorem is, again an important theorem is, in normal, so let f be a subfamily of omega if this family f is normal in omega, then f is locally bounded. Omega. Okay, so this is the result. Okay, so this we can prove basically. Let us try this one. Let's prove this theorem. Okay, so we have a subfamily which is normal. We have to show that it is locally bounded in omega. So this is a just keep in mind that this is a family of continuous functions. Okay, so suppose the statement is not true. False. That is, so we have to show that it is locally bounded in omega. Locally bounded means there exists means locally bounded in omega means on every compact subset K it is uniformly bounded. So if it is not locally bounded omega means there exists a compact subset where it is not uniformly bounded. That is, uh, there exists there exists a compact set K in omega on which f is not uniformly bounded. Okay, so then for each positive integer teaser positive integer f, if is positive integer n, we choose a function fn and points zn subset of k such that modulus of fn at this point zn is less than equals to n. Okay, this we can do because this is not uniformly bounded on k. Okay, fine. The Now since f is normal, this family is normal f, the normality of f enables us to extract from the sequence fn a subsequence fnk, okay, that converges normally in omega, say to a limit function f in c omega. Okay, now let m is basically maximum of mod of fz where z belongs to k, maximum over k f of z. Okay, since basically f and k converges f uniformly on k. Okay, basically f and k converges f to normally in omega, means it will converge uniformly on k, uniformly on k. Okay, there is an index k naught. Okay, k naught with the property that when k is greater than equals to k naught, f and k z minus f of z is less than 1 for every z belongs to k and for every k belongs to k naught. Okay, so this we are using the uniform convergence. Okay, so f and k z minus f of z, so let epsilon be 1, so f and k z minus f z is this happens. Okay, for this one. Okay, now nk, okay, is less than equals to f and k and this point z and k. Okay, by this one, by this thing, so by one, so by one. Okay, and again this quantity is less than equals to, okay, this, basically this quantity is equals to this one. Okay, what I'm going to write, so in a whole this quantity will be, okay, so this is f and k z and k minus f z and k plus f z and k. Okay, which is again less than equals to f and k z and k minus f of z and k plus modulus of z and k. Okay, now nk is less than equals to, so this is, wait a minute, so this will be less than 1. Okay, and this will be less than m, so this is 1 plus m, which is a contradiction. Okay, because nk tends to infinity, as we see here. Okay, here, so this is a contradiction on the fact that, so this is a contradiction, to the fact that nk tends to infinity as k tends to infinity. Okay? So thus we thus conclude that f must be locally bounded. So we conclude that f must be locally bounded, in omega. Okay. Now we are going to talk about the space of analytic functions. So any doubt? Okay, so we'll move ahead. Okay, now the next thing is space of analytic functions. So space of, okay, okay, so let omega be a domain, denote h omega, H omega is basically F such that omega to C such that F is analytic. Okay, so clearly H omega is a subset of C omega, isn't it? Okay, so now the question is H, the question is, wait, so now the question is H omega is closed in C omega, closed in C omega. Okay, so we'll prove that H omega is basically a closed subset of C omega. That's the important thing. So answer is H omega is indeed closed in C omega. Closed. Okay. So for this, what we need to do? So we need to prove that. So if a sequence Fn in H omega converges to F, we have to prove that F is again in H omega. Okay. So what we need to prove? So let Fn be a sequence in H omega. Okay. Or you can also write Fn be a sequence in H omega such that Fn converges to F normally in omega. Okay, so claim is F also belongs to H omega. Okay, so proof is, so for this one, proof of claim. So we have already seen that F is continuous. Okay, now we have to prove that it is analytic. We use Morera's theorem. Morera's theorem. Okay, let gamma be any closed rectifiable curve in omega. Okay, so what do we need to prove? Sorry, not close. So we will prove it for so we will use Morera's theorem to prove this one. So let D be any disk in omega. Okay, just wait a minute. This is omega and gamma be any closed gamma be any closed rectifiable curve in D. Okay, then just wait better to use the rectangle version. So let R be any closed rectangle in omega. Okay, so R being closed rectangle. So by Cauchy's theorem for rectangles, so we have fnz dz over this boundary of the rectangle is equals to 0 for every n. Okay, and since fn converges to f normally, okay, we have integral over boundary of r fz dz is basically limit n tends to infinity fnz dz. Okay, so this is basically 0, and hence by Morera's theorem we have f belongs to the h omega. Okay, so basically this is Sn is closed, hence h omega is closed in c omega. Okay, moreover we can also prove, moreover f and k, okay, also converges to fk normally, omega for each k greater than equals to 1. Okay, means derivative also converges to the derivative of that one. Okay, this is the standard result. This one should try to prove. I mean, this is important. This is important. Okay. Now I will state a more important theorem, which is known as Montel's theorem. Okay. So the statement is like this: let let f now a family of h omega. Okay. F is normal family if and only if f is locally bounded. Okay, so like we have already proved that in the case of continuous family, that if f is a normal family, it is locally bounded. Okay, in the case of continuous family, so it will hold for not also for this one. But locally boundedness in the space of, if this is just a family of continuous functions, then locally bounded doesn't imply that it is a normal family. But once it is becoming the analytic function, family of analytic function, locally bounded implies the normal family. Okay, this is quite an okay, let us try to prove this one. Okay, so, f is subset of h omega. That, so f is also a subset of c omega, and we know that if f is a normal family, then it is locally bounded. So basically Monte's theorem is about the converse of this one. Locally bounded, then normal family. Okay, so now let f is locally bounded in omega. Okay, so clearly f is pointwise bounded also. So in view of Zilla Sole, we only need to prove that f is equicontinuous. Okay, so this can be done. So we fix z naught belongs to omega, and and we show that this family f is equicontinuous at z naught. Okay, so this is the main idea. Okay, so for this we choose R positive with the property that this K is basically this ball is subset of omega. So by hypothesis, there is the hypothesis is there exists a constant m which only depends upon this compact set K positive, such that mod of fz is less than equals to m for every z belongs to K, and for every f belongs to this family f. Okay, so now what we are going to do, for z belongs to this ball R, and gamma is such that z minus z naught is equals to basically 2R. Okay, we are going to calculate something. So fz minus f of z naught is basically, we can write 2 pi outside, and we can basically write integral over gamma f xi minus z d xi minus integral over gamma f xi upon xi minus z naught d xi. Okay, so this is now 1 upon 2 pi integral over gamma. So f of xi into z minus z naught upon xi minus z into xi minus z naught into d xi. Okay, and this is basically mod of z minus z naught upon 2 pi. Okay, and integral over gamma f xi d xi upon xi minus z into xi minus z naught. Okay, okay, so now this is less than equals to m into z minus z naught upon 2 pi integral over gamma. uh, this is going to be mod d xi upon mod xi minus z into mod xi minus z naught. Okay, so Now, okay, so xi minus z naught. Okay, so z naught is in this ball. Okay, so and xi is on this curve gamma. So xi minus z naught will always be, okay, so this will be 2r. Okay, yeah, so this will be 2r, and this xi minus z is always greater than equals to r for every z belongs to this ball. Okay, this is quite clear. So 1 upon modulus of xi minus z into xi minus z naught is basically 1 upon 2r square less than equals to 1 upon 2r square. So this we are going to use it here. So this gives that modulus of fz minus fz naught is less than equals to m mod of z minus z naught upon 2 pi and 1 upon 2r square integral over gamma mod d psi. Okay, so this is now less than equals to z minus z naught 2 pi upon 2r square, and uh, this will be 2 pi into 2r. Okay, so now fz minus f of z naught, this will be less than equals to m mod z minus z naught upon r. Okay, so now we are done. So for given epsilon positive, let delta is your minimum of r comma r epsilon by m. Okay, so such that we will have mod of fz minus f of z naught is less than epsilon whenever, so such that for every f belongs to f we have this whenever z minus z naught is less than delta. Hence f is equicontinuous continuous at z naught. Okay, and since z naught is arbitrary, f is equicontinuous in omega and normality follows. Okay, so this is done. Moulton's theorem and its proof. So this is quite an important theorem. Just wait a minute. Okay, so I will just add this as a exercise. Or so this also one can consider theorem. Let f subset of h omega. Okay, so if this is normal, then the family f dash, which is nothing but consider f dash such that f belongs to, you just consider derivatives. Okay, then this is normal. Okay, so this is a theorem and this is easy to prove, there is nothing to it. Now the question is, what about converse? Okay, so I mean, see this, if we take fn such that c to c by f and z is basically n for every z belongs to C. Okay, so clearly we can see that your f is, you just take fn such that n belongs to n. Okay, so we can see that f dash is nothing but only the zero function. Okay, so which is again normal family, but f is not a normal family. Okay, but the converse is true. Converse is, but for the converse we have the following theorem. Theorem is like, so let f be a family of analytic function, and first suppose f dash is normal, second, and second condition is f of a such that f belongs to f is bounded for some a belongs to omega. Okay, if these two condition holds, then f is normal. So this is the statement for the converse. Okay, so we are done with today's assignment, today extra session. Any doubt, please let me know. Subhasri, any doubt? Hello, can you hear me? Okay, so there is no doubt, I will consider that it is fine. Okay, so thank you. I am going to end this session.